Okay, in the last video, we showed that we could build a charge distribution from individual charges. And in doing so, we could determine the work that's required to build up that charge distribution. We found the following equation. The work was the sum of I, QI, VI at some point PI. Okay, where the potential is the potential due to the charge distribution that you're trying to assemble, right? And there's a 1/2 out front that accounts for double counting, right? Because that charge is already part of the charge distribution that you're looking at. All right, so this Q here, right, if it's really small, of course, with the sum, we can take advantage of the Riemann sum to turn this into an integral, right, such that the work is equal to 1/2 the integral of the charge distribution times V times d3x. So I take the charge distribution times the electric potential and I integrate it over the volume, right? And that will tell me the amount of energy that's stored in the system. Okay. Not that terrible of a calculation. But, so that's telling us that the energy is stored by these interacting charges, right? That I put the charges together, right? And they're somehow interacting, right? The interaction here and the interaction there, somehow there's some energy there, right? And to calculate it, I simply do this thing right here, and that'll tell me the total energy that is encompassed in that system. All right. Now what we're going to do is we're going to go on a mathematical mission, and we're going to show that another form of the energy, and it's going to have major consequences. All right, so we look at the charge distribution, right? So the charge density is going to be, we know that that is going to be the divergence of E is equal to the charge distribution over epsilon naught. So if I rearrange, you get the charge distribution is epsilon naught times the divergence of E. Okay. Now, we're going to go on a mission. It's going to be intense. I want to say something here, and this is really important. These kinds of things take physicists a whole lifetime to develop. They make many mistakes, they try many things. A lot of times things don't work. So when you're studying this and you're struggling with it and thinking, how would they ever come up with this? I can't. Think about that. You're trying to learn what they took a lifetime to learn in a couple of hours, right? So we're going to build up your knowledge so that you're kind of at the state of the art when you leave college and you're ready to go out and to do those things that are going to be really hard. But the students that come in the future are going to take your work, which you take a lifetime to do, and a whole community of people working on it, and they're going to learn it in a few hours. So don't be too stressed if you don't get this at first. This is hard. It takes a lot of mental power in order to come up with this. So go through it, learn it at your own pace. Okay, what we're going to do is we're going to take this and we're going to plug it in for the charge density. So let's do that. The divergence of E, right? Of course, the divergence of E is a scalar, right? And we're left with this somewhat ugly equation. Okay, now, again, we're going to do something really bizarre. Okay, we're going to look at the following vector identity. we're going to look at the divergence of a scalar, f, times a vector. And we're going to apply a vector identity to that. All right, so when I take this, remember that del is just the partial of x in the I hat direction plus the partial of y in the j hat direction, and so on. Right? Dot f, which is some function of x and y, and g, which is going to be gx I hat plus gy j hat. So when I do the dot product, I'm only going to care about getting the I hat terms and the I hat terms, of course. F is a scalar, and when I distribute this in, it's going to be in on both terms. So I'm going to have d dx of f gx plus d dy of f gy. Okay? And now, since both f and gx could depend on x, I have to use the product rule. The same thing here with f and gy. So I get two terms, gx times the partial of f with respect to x plus f gx partial with respect to x plus gy df dy plus f dgy over dy. So this thing becomes four terms. Now if I look at it and I group this term and this term together, that's going to look a lot like the following. It's going to look like G dotted into the del acting on F. And if I look at this term, these guys, that's going to look a lot like F acting on the divergence of G. All right, take a minute, think through that. All right, remember that F is a scalar and G is a vector. Right, so if I call my scalar V and I call my vector E, I get the following. VE, right, acting on all of that, is going to be equivalent to this, which is going to be E dot del V plus here, which is going to be now V, the divergence of E. So I can take this term and bring it onto that side, and I get that V, the divergence of E, is equal to this term, the divergence of VE, minus E. Now, what is going to be del acting on V? Well, that is just dotted. That's going to be minus E, right? Because the gradient of the scalar field, the electric potential, is just the electric field. Or minus times a minus, this becomes plus E squared. So I can take this thing and plug it in there for that term here, because this and this are the same. So when I do that, I get the following. I get the divergence of VE plus E squared d3 dx. And of course there is an epsilon naught here, right? Because there was an epsilon naught before that I had to pull out, and I didn't have the epsilon naught in here in this part. Okay, so looking at this, this gives me two integrals I have to do. I have to do this integral with e squared, and I have to do this integral here with all that mumbo jumbo. So let's start with the mumbo jumbo integral first. So that's going to be the divergence of v acting on e d3x. What is that integral? Okay, so what I'm going to do is, this is a scalar times a vector, but that is also a vector, right? A scalar times a vector is a vector. And so I know that if I have the divergence of a vector integrated over a volume, that this is, just taking advantage of Green's theorem, the integral of that vector, which in this case is v times e, dotted into the surface area of your volume. Now we do something really wacky. We let our area go to infinity. We choose an area that's so big that it encompasses the entire universe. Let's think how these three quantities go when the radius goes to infinity. Okay, the area, the surface area, is something like 4 pi r squared. So the surface area goes to infinity when the radius goes to infinity, right? So if I let the radius go to infinity, I have infinite surface area. The electric field, if I go far enough away from the charge distribution, it looks just like one big charge. So you would expect this to go as 1 over r squared, right? So as I go to infinity, it's going to fall off with this 1 over r squared dependence. And of course, if r is infinity, it's going to go to 0 at infinity. And we know that the potential goes as 1 over r, right? It also goes to 0, but in a less slow manner than the electric field does. So I take 1 over r squared times r squared, right? And that gives me something that is going to go as 1 over r. So if I take the surface area to infinity, I expect this term to go to 0. Because the radius becomes infinitely large. So what's cool is that makes this integral easier. That integral becomes just the following. The caveat is that I have to do this integral over all space, right? Because the only way I could make that approximation to make that go to 0 is if I included everything. So if I include everything, that term goes to 0, and I can determine the total energy by just squaring the E field. This is one of those holy shit moments in physics. I started with particles interacting. The particles were generating the energy between them, right? The potential energy. But, really important, there's an alternative view of viewing this. That the energy in the charge distribution is actually associated with the electric field. So that there's a field that's generated by charges interacting. And the energy, the potential energy in the system, is stored in that field.